All right, guys. Now we need to talk about enthalpy. Enthalpy is it's a technical thing in thermodynamics, but it's super important. I- its symbol is H. Don't ask, I didn't come up with it, but simply put, it's heat. But it has to do with changes of energy and entropy and pressure and different things. But we're just going to kind of refer to it as heat. The processes involve change of enthalpy. So anything that happens involves a change of enthalpy. Delta means change. So we have like nobody knows the exact value of enthalpy. Sort of like when you climb a ladder, you just say like you've gone up 10 feet. That's it. But if we really wanted to be specific, we would say, what's your height from the center of the earth? But nobody really cares because you just care about the change in height from the center of the earth. And so that's what we have here. It's measured in kilojoules, and we have our endothermic and exothermic processes here. So an example of this would be down here. Water burns, right? Or excuse me, hydrogen burns with oxygen to form water, all right? The delta H for this reaction, or the heat of this reaction, is negative 286 kilojoules. What you must do is balance this equation first. I hope you understand that. When we balance this equation, we get two H2s plus an O2 gives us two H2Os. This number stays the same, okay? This is for the balanced equation, same. Okay, here. What is the delta H if 4 moles of H2 burn? Utilize this like stoichiometry. It's the same idea. You have 4 moles of H2. See, I got it from right there. See? Okay, right here. This conversion factor right in here, that negative 286, that comes from this delta H, and it's over 2 moles of hydrogen. You might ask, Mr. Beck, where'd you get the 2? Right here. This is your 2 moles of hydrogen. Should do that. 4 times negative 286 kilojoules divided by 2 gives us negative 572 kilojoules. This should make sense because the more hydrogen you burn, the more energy you give off. So we treat it like stoichiometry. All right, now bomb calorimetry. I'm not going to give you any problems with this, but it's something I think you should understand. This is how we measure calories for food. So if you ever look at the packaging for food, this is how we figure out the number of calories. 1 calorie equals 4.184 kilojoules because essentially what you're doing is when you eat food, you're ingesting calories, you're ingesting energy. So here, the way that this thing's set up, I've been asked many times before, like, can we build one of these? No, we cannot. Every website says, whatever you do, don't build one of these on your own. You have this ignition coil in here. This is like this is your box where your sample is. It's supposed to be a Cheerio. And it's surrounded by water because we understand water pretty well. And you have a thermometer here. So what you end up doing here is you measure the temperature of the water, you ignite this sample, so you just like burn your Cheerio, and then you measure the new temperature of water. And because of that, what you get is this. The heat of the reaction, that thing that got burned, is negative. This big C is just, instead of specific heat for water, the whole uh, instrument has a heat capacity, so it takes mass out of the equation. So we get C times our change in temperature, which we use a thermometer for. So that's what we have. And this, don't worry about problem set 4. We're not going to do anything with this. It's just so that you understand when you look at the side of your Honey Nut Cheerios or your Pop Tarts or whatever you're eating, this is how we know how many calories are in there. We're basing that number on if you set the whole Pop Tart on fire, how much, like, what would the temperature change be for water? So that's what we have here. This is bomb calorimetry. All right. When you look at those problem sets that I'm going to give you, there's 3 problem sets. I'm going to give you an example of each type, and I'm going to put those notes up. I'm not really going to walk through it. They're just going to be on Canvas. All right.